Professor Greg Pasternak, and this is a video podcast lecture for HYD 151, Field Methods in Hydrology. The topic for this video podcast is snow measurement and sampling. And, snow is a major form of precipitation. In mountain-based regions like we're in here in California, you may have a lowland that's relatively dry, but the water supply for that could be partially or primarily coming from the snow region in the mountains. And so that's why it's really important to be able to characterize snow where you have, say, a lot of topographic variability or spatial complexity to the distribution of snow. There are also large, flat or rolling regions in more, high continental areas that also have large amounts of snow, and where obviously then snow could also be a major contributor to water supply. But the difference is in those regions you also tend to have higher total precipitation, whereas in a mountain-fed, dry or Mediterranean area, you have very low total precipitation, and so the relative amount of precipitation as snow in the mountains is disproportionately important. When you look at the photo that's shown on this first slide, one of the interesting attributes of snow that makes it quite different from other forms of precipitation is its ability to accumulate on a surface disproportionately. So water or hail would otherwise be dripping off or rolling off or just not accumulating at all, but the surface tension on snow allows it to accumulate, and so then that becomes one of the interesting properties where you can have a lot of storage there. You can also see that there can be a differential if it's being held up in the canopy. Then what does that mean for what's happening underneath in the canopy? And so that's important as well. So for example, you might wonder, do you get more total water stored in a snow area that's forested or clear-cut? So these are the kinds of things that are of interest to understand with snow hydrology, and so we need to have good methods for measuring snow. As always, I like to show the distribution of something that we're going to be measuring, and when we look at the United States distribution of snow, you can see that it's generally governed by two variables. One is the latitudinal gradient, so you're going to have more snow accumulation in northern latitudes and less in lower latitudes. And then secondly, you'll have the highest at high elevations and then less at lower elevations. Now, this would be a good time for you to pause this video podcast, go back to the lecture on precipitation from the last time, and look at the distribution of precipitation as a whole. It's quite different because precipitation has more of an east-west distribution for the United States, where when you come off the mountains, then you have a loss because you have the jet stream and the atmospheric circulation that's carrying moisture from the Pacific Ocean over the mountains, and by the time it gets all over the mountains, it's fairly dissipated. Then you need to have water coming up from the south, from the Gulf of Mexico or from the Atlantic to bring moisture back in. And so you get this east-west barrier between moisture that is coming from the Pacific versus moisture that's coming from the Gulf of Mexico and the Atlantic, as well as a little bit from the Great Lakes to the north. So there's a really different pattern between overall precipitation and what you see with rainfall, with snow. At the national level here in the United States, there is a mandate in the 1930s to measure snowpack in the mountains of the West and forecast the water supply. As a result, the National Resources Conservation Service, they install, operate, and maintain an extensive network of automated systems called SNOTEL, which stands for Snowpack Telemetry. This is a system which today has more than 750. I know on the slide it says 730, but it's changed and now it's more than 750. And those numbers grow as long as the funding remains high. And at these automated stations, they're collecting snowpack data and other general weather climatic information for the western United States. And then this is all telemetered back to a central storage that you can access on the internet at the web address that's shown at the bottom of the slide. So the basic SNOTEL sites have a pressure sensing snow pillow, and I'll explain what that is shortly, a storage precipitation gauge, and an air temperature sensor, and they're recording data every 15 minutes. There are other types of snow data that I'll be showing you in this lecture, and that also is incorporated into the National Resource Climate Service Data Center, this NRCS. Here's a map that illustrates SNOTEL data, and it's just illustrating for a particular day relative, with respect to 1990 to 2004 average on this particular data of January 9th, 2010. When you look at the western U.S., blue is indicating high above average, and red is indicating below average. And you can see that on that particular day, there was some precipitation or snow, in the southern western U.S., but generally actually relatively low compared to total average conditions. Now, when you look at this pattern of dots, one of the interesting things is it's highly irregular. Like if you knew nothing about the surface, you might say, well, why is this not using a uniform grid? Because a uniform grid can give you the best overall coverage with the least interdependence between sites. It's also not random either, but the reason for this pattern is first, funding considerations. So who's going to pay for these sensors, and finding partners. So you might have more sensors, say, like at ski resorts where there's already a private interest, and there might be some value in leveraging the federal funding and local funding, or just near towns that are in the mountains. And then very remote areas, or areas, of course, of very low elevation that are not receiving much snow, wouldn't have much coverage. Within California, the 1929 California State Legislature, they established a statewide program that's still used today. California Water Code Section 228 says, "The department shall gather and correlate information and data pertinent to an annual forecast of seasonal water crop, including the making of snow surveys, either independently or in cooperation with any person or any county, state, federal, or other agency." And this data is provided on the CDEC website, which the link is shown below. One of the types of information that you'll see is called a snow course. This is a method that's been long used in California, and there's over 300 snow courses here in California. The snow course consists of a transect along which 10 measurements are made. The transects are all 1,000 feet long. And this is an example of a map of a snow course to just give you a feel for what they're like. So in this case, you have a topographic map that gives you the general vicinity. It shows you some local roads and trees. And then the measurement is made from this particular 42-inch white fir and then across to this 16-inch ponderosa heading in that direction. The spacing between the stations, you see you go 50 feet to the first station, and then 25 feet, and then 50-foot intervals, a 75-foot interval, and so on. So generally the intervals are 25, 50, or 75 feet, obviously trying to avoid a road or other structures. And so, this is the overall transect, and there are more than 300 of these in California. At each location on the transect, each of these 10 locations, a snow accumulation measurement is made. Now, in all the lectures that I show in this class, there's always one method that is the most basic, manual approach, and this is it for this technology. What you do here is you take this aluminum tube, which is shown in the middle, and you shove that down into the snow until you get to the point of resistance, and hopefully the point of resistance is the underlying ground. Once you get to the ground level, then you extract the core, you pull it out, and you clean the dirt out of the bottom, and then you basically turn it on its side and weigh it with a scale that you have in the field. The scale is pre-calibrated so that after you subtract the empty weight of the tube, 1 ounce of weight corresponds with 1 inch of water depth equivalent. So that is, if you were to melt the snow, it's the weight of that. So the weight doesn't change whether it's snow or liquid. It's just giving you that weight. So the main advantage is it's very simple and it's easy. It's a direct measurement. You could imagine that if you had like 30 or 40 feet of snow that you would probably not be able to push in with tubing that far. It's theoretically possible. You just need more sophisticated, coring capabilities, because you can't even just hold up a 40-foot long tube very easily. But you could have sections and put them together. So the disadvantages here is it is a manual method. As you can see, you have to snowshoe out to these remote locations, and that leads to a tendency to only want to make measurements that are accessible and safe, relatively low transportation and time to have to get to those locations. And then you're only getting a point measurement, and if you have an entire mountain range like the Sierra Mountains, even with 300 points, does that even begin to scratch the surface for what this is? But that's what the method is, and it is highly used. When you have a snow course, then what you do is you take the data and you record it onto a sheet manually, and I'm sure this could also be done on a handheld data collector today. Here are two different individual sheets from about 15 years ago. What you can see is that each sampling location is noted, the depth of snow in inches, and then the length of the core in inches. Now notice that the core, if you have a tube and you push it down into the ground, we're not talking about the length of the tube. You could take the tube out, and then you can put a ruler inside the tube and see how much of the tube has no core in it, and then that gives you the total length of the core, which is what you have here, right? So you have let's say you have a 100-inch tube, and 16 inches have no snow in it. Then the length of the core is 84 inches. However, if you put the ruler into the hole, you may find that you went down 89 inches. And the difference between the depth of the snow and the length of the actual core is compaction. Because when you push, that snow is going to smush together inside that tube, and so you have compaction. It's theoretically possible to have expansion, but that's usually true with clay swelling or something like that, not so much with snow. With snow, you're most likely to have a compactionary effect. But we're not interested in the raw length of this or necessarily even the depth of the snow. We're interested in what we call the snow-water equivalent, which is if you were to melt the snow, how many inches of water would you have of that melted snow? So to get that, you begin with knowing the weight of the empty tube, which is 53 ounces in this case. You weigh the tube and the snow, and you get 89 inches. You take the difference of those two, which is that was 89 ounces. The difference of the two is 36 ounces of weight, and as I showed on the previous slide, there's a 1 inch to 1 ounce conversion for water content. And so this is repeated 10 times, and since it's 10, you just sum all these numbers up, take the average, and you get 314 is the sum, so 31.4 is the average. And if you take the depth of snow and you take the water content in inches and you divide those one into the other, you find out that the density of the core here is about 42%. On the right is another example from a snow course, but it's one that has relatively little snow in it. You can see that there's only an average of about 13 inches of depth of snow, and there's not enough weight to register always, and so it's here. It's kind of like the total. The total of all of that was 54, and so the average is only 3.7 inches. Okay, well, I'd like to show you some other ways of doing it. For example, let's say you have a very large rolling, continental region. So here's a map of, the area of islands off of Greenland and northeastern Canada. And there's this big Fosheim Peninsula, as well as this other island here. And then they need to measure the snow in this area. So let me read this to you. It says, the snow surveys were carried out by 2 persons on snowmobiles. In the field where snow cover rendered most landscape features hard to recognize, transect lines were located using a combination of GPS and aerial photographs. So the key here is you have this vast area, you need to have snowmobiles to get around, and then you're going to distribute your points still on transects because it's easiest to do that, but you then need GPS to find those locations. And you remember from our GPS little experiment that that's going to get you within 1 to 2 meters of your site. The length of the transects varied from tens of meters to several kilometers, so still relatively small compared to the totality of the area. Transects were typically a straight line across the terrain, with snow depth samples taken at regular intervals. So here, that sounds like a snow course, just having to do snowmobiles, but look what they do at each site. So first, they are mindful of the terrain in this case. There are stops on a valley transect about 10 meters apart, but then for larger areas they could be 30 to 50 meters apart. And then at each stop, instead of taking one measurement, now they're taking 4 measurements on the corners of a 15 meter by 15 meter square. And then here the snow depth was measured by just putting a steel rod down, and snow density was measured using a snow sampler. So you can see that this is a little bit different approach, but it has some similar themes. It just accounts for different kinds of terrain. A snow pillow is a more advanced technology. It has some limitations too, but what a snow pillow is you take plastic and you create pockets within the plastic and you fill them with antifreeze. And then you can see in this case there are 5 independent pockets, but they're all plumbed together with tubing, so it basically makes one overall mass of fluid that's equilibrated between the two. And you lay this out and connect it to a data logger, and then as snow accumulates on top of that, the weight pushes down and it pressurizes the antifreeze. And that pressure is recorded with a pressure transducer, and then that the pressure transducer transmits that to a data logger, and then the data logger can send that to a transmitter to transmit it back to central data repository. So one of the downsides with the snow pillow is that if the snow were to pile up and somehow form an arch over the snow pillow or create gaps where it isn't having good contact with the pillow, then that kind of archway effect could lead to not recording the pressure that's there, because the pressure could be dissipated away from the pillow itself. So if for some reason there was preferential melting on the pillow. Here's an example of snow pillow data from one site. What you can see here are months on the x-axis, and then the accumulated amount of snow, snow water equivalent in millimeters on the y-axis. And you see many different lines. The pink line with the black diamonds is showing the maximum in the record at this site. The yellow, the dark yellow with the pluses, is showing the minimum for the site. The blue with those funny symbols is showing the average. The circles shows what happened last year for this data. And then the X's, which are really hard to see because they overlap a lot, but you can see here, right along here, the X's are representing this year's data. And so it looks like for a period of time, the X's here were showing the absolute, a new low, a new minimum for this site. And so it's a relatively dry location. Now, one of the things is that you're measuring the weight with the snow pillow, and so that weight has to then be converted to a depth with a snow water equivalent. So on the bottom here, I've shown how you do that. If you know that you have 1 kilogram of snow, then you can convert that to a snow water equivalent by using the density of water. So here we don't care about the fact that the snow itself has air in it or anything like that, because we're just melting it. So we multiply that by the density of water, 1 cubic meter per 1,000 kilograms, and then you have to divide that by the area of the snow pillow in square meters. And so you're crossing out kilograms here, and you have cubic meters of snow water equivalent per unit area. And so that ends up with a meter of snow, or snow water equivalent. Another technology for measuring snowpack is called a snow tower. So with a snow tower, you have these metal plates. There's 24 plates spaced up the tower in equal distances, And these can be distributed in a mountainous region, and then one can fly over in an airplane, and in this case you count the visible plates downward. You know there's 24, so in this case you see 1, 2, 3, 4, 5, let's say. So you know that there's 19 that are under the snow, and so you can know how thick the snow is. So the main advantage of this technique, of course, it's fast. You can cover a large area. It's still a point measurement though, and you don't know what the density of the snow is, so you can't necessarily convert it to a snow water equivalent. However, for California in general, during the main snow season, the density is about 12%, and then later in the year it's about 33%. So you could use these general rules of thumb to do a conversion if you want to. And then there's also remote sensing of snow, and this is also very important. What remote sensing does, it tells you the area of snow, but it can't tell you anything about the thickness or the density of the snow. There's a sensor called the Moderate Resolution Imaging Spectroradiometer, or MODIS. It's a 36-channel visible to thermal infrared sensor, and there's a variety of different snow and ice products from the sensors. But one of the things you can do is, if you just look here at this particular view of some of the sensors here, you can see that the snow is showing up as this bluish green color. And it's pretty easy with an algorithm to convert that to just a black and white absence or presence, where white is presence of snow. And you can see at these 3 different time intervals the different amounts of snow. And I've used MODIS in the Sierras. It's actually a highly accurate product that we can use to calibrate the percent cover of snow compared to spatially distributed hydrological models. Okay, so now what I want to do is just illustrate how some of these different sensors are used in actual studies of snow and snowmelt, just to give you a feel for their context. So we don't have a snow field trip in the course right now, but it's still good to get a feel for how these are actually deployed. So here's a case from a analysis that's done in the Western Cascades of Oregon, asking how snow accumulation and subsequent melt during a rainfall event compare between forested and clear-cut plots in a transient snow zone. So that means, transient meaning that it's not always snow-covered during the winter. And here's an aerial photo that shows the region that we're looking at, as well as the watershed map that's there. And this was all done at the H.J. Andrews Experimental Forest, where a lot of work is done by professors at the University of Oregon and Oregon State University. So at this particular site, what you can see is there are individual trees, which are shown by the canopy of the tree is shown by the big diameter circles, and then the tree trunks are shown as the smaller circles with the marks on them. And then under the canopy, there's one tipping bucket gauge, which has a funnel network that runs these flat half-meter by half-meter pans. And these pans are on the ground, and whatever snow hits the pan is melted because these pans are heated. And so when it melts, then the water runs down the funnel network to the tipping bucket gauge. So this is an innovative way to use one tipping bucket gauge to measure the snowpack in 8 different areas. You can see that some of these are near tree trunks, some are out away from canopy. So you get a different kind of open and canopy conditions. It's also possible, not in this study, but in other studies, you'll see that you might randomize these locations over the course of a study. You also see out here other kinds of sensors, an anemometer for wind speed, a wind direction sensor, soil temperature, air temperature, a movie camera that's at least taking time-lapse shots every 15 minutes, and then there's a rain gauge, and then a pyranometer is a device for measuring incoming shortwave radiation. So that's kind of like a sensible heat flux that's going to be able to tell you what heat the snow is experiencing. In this case, the sensors are sampled every 10 seconds, but still, the actual snow conditions, are not going to be changing that fast. So comparing the clear cut versus the forest plot, this study was done in 1982, 1983. you could see on some individual dates how the depth of snow was actually relatively high, anywhere from, looks like, well, the low of 30 millimeters, but, highs of, 200, 500, 250 or so millimeters. So quite, typically more than 100 millimeters of snow in the clear-cut plot. Whereas on the ground in the forest plot, it was patchy, some places with no snow, a maximum of 123 millimeters. So generally, much greater depth of snow in the clear cut than in the forest area. If we look at the snow water equivalent, it's relatively high, again, in proportion to the total depth. But if you take the average of those and you get the density, not the average, you divide one into the other and you look at the density, then what you can see is that the density in the clear cut plot ranges from about 15 to 50, whereas the snow water equivalent is a little bit higher, but where there is snow, I don't know, it seems to be relatively similar actually to me. But oh wait, I'm looking at the wrong column, yeah. That's why. Okay, so it's generally, you can see in the 30 to 50 range, yeah. So you see it's more steady and on average higher than it is in this case here. The free water contents also, where you have water, are a little bit higher, but again, that's only where you have it. So there's a clear difference. The clear-cut plot has a lot more snow on the ground than the forested plot. Where's the snow in the forested plot? Up in the canopy. So it's not much of a surprise. However, it's a significant difference because what happens to the snow in the canopy? So to summarize those results, the clear cut accumulated much more snow than the forest, and then the forest snow turned out it's intercepted in the canopy and it's evaporated away. So that evaporated water is then lost from a water supply perspective. So from that perspective, if you want to make a really simple answer, if you live in a mountainous region and you want to have lots of snow for later water supply use, you'd want to cut down the forest. That's a very simple answer, but that's the reality of that. At the same time, we will see other weather-related effects, so we don't have the full answer just yet. Now, the clear-cut outflow was 20% higher than the forest outflow. So that means that for the snow that is stored on the ground, it is protected by the presence of the canopy. The total energy available in the clear cut was 40% greater than that in the forest. And the clear cut had higher wind speed, sensible heat, and higher evaporation rate. So let's look at some of the high frequency time series results. Here is what happened during a rain event on the snowpack. So the solid line is what happened for the clear cut, and then the dashed line is for the forested plot. So precipitation actually reaching the ground was greater in the initial stages of this rainfall event for the clear cut because the canopy held that water. So the water goes into the canopy and goes into the snow. It is rainwater, but the snow itself has a storage capacity, as does the snow on the ground, but the water's making it to the ground in the clear cut. After a while, the rain slows down, but water is now dripping out of the canopy towards the ground, and so then that acts like a precipitation event that's affecting that. You can see that after that, the precipitation continues, and it's fairly similar between the two, so there isn't so much difference. A lysimeter is a device for measuring the outflow, in the soil. And we'll talk about that later on in the quarter. What you can see here is that there is a lot more outflow that's taking place from the forested plot initially. So in this case, the extra water that's raining onto the ground is being taken up as storage into the snowpack, and it isn't really being released. Whereas here, this water that's dripping off, it's already oversaturating the canopy, right? That's why it's dripping out. You have meltwater coming out of the canopy. When it hits the ground, there's relatively little snow on the ground, and so it's already running off. However, when you look at the totality of the storm, you can see that the solid line rides above the dashed line, and so that's telling us that there's more overall runoff that's coming from the clear cut than from the forested area. When we look at the weather sensors, there's some effects that we see here. Now this top one is really hard to see because there's so many different kinds of dashing. So the solid line is the air temperature in the clear cut, okay? And then the thickest, no, let's see, wait, okay. There's like an intermediate air temperature that's for the forest. So the solid line you can see starts here at 0 because the clear cut plot air temperature right above the ground is 0. It's pretty much 0. Now the air temperature of the clear cut is up. It's one of these lines here. It's this line up above. The soil temperature for the clear cut is on top of the air temperature. So the air and soil are at the same temperature of about 0. The soil temperature of the forest is actually warmer than the air temperature of the forest, just a little bit. Now what you can see is those two stay relatively flat for quite a long time. Eventually the soil temperature goes up and the air temperature goes up later. However, if you look at the clear cut, the air temperature and soil temperature go up first. They cross over, so you have this like reversal, and you then have much warmer temperatures in the soil and air in the clear cut for a very long time compared to what's happening in the forested plot. So there's a temperature difference. At the same time, there's a significant difference in net shortwave radiation heading into the clear cut compared to the forest. And so the result of all of that is that if you look at the outflow from the lysimeters, is you're going to have more runoff from the clear cut than the forest. So let's just think about this. Let's take a step back from a methods perspective. We've got a lot of data here. We have a relatively small site, and we're left with making these interpretations. We're trying to get at the mechanisms. We started off with the raw, what's the final result we're seeing? Okay, we're seeing the change in snow water equivalent. That gives us the simplest, most direct answer to what's happening in the study. But when you want to start to explain that, now you start looking into the time series, and it starts to get more complicated. Then we have to look into the energy balance, and it becomes more complicated. And by more complicated, what I mean to say is it's more interpretive. We're using heuristics to try to explain this in a mechanistic way. We could probably extract specific quantitative metrics. That would probably be a good way to help nail this down. But overall, it is still fairly interpretive. So the alternative would be then to run a computer simulation of the snow balance at this particular plot and then see if you could replicate these results. But you can see that the way a hydrologist thinks is to make measurements, to explain those measurements in terms of the underlying mechanisms driven by precipitation and energy fluxes, and then to make a model to try to see if you could replicate those results. Okay, I want to show you two last examples of snow information. So here's an experimental study where we want to see how different species of trees can store snow in their canopies. And so here, this is the gallows approach to hydrology. You take a tree and you cut it off at its base and you hang it on a tower using a load cell. The load cell has the ability to measure the weight of whatever is hanging on it. Once you have the dry tree hanging, then you zero it because you're not interested in that. And you may even use springs to offset the weight because you don't care about the weight of the tree primarily. You care about ultimately the weight of the snow. So as snow is intercepted, you can get a time series that shows you the weight. And if you separately measure the snow, you can see the accumulation of snow, and then you can see the evaporation of it and what's driving that. And you can do that for different species of trees. So here are the results for a jack pine in 1994 and a black spruce in 1992-93. And you can see that the top graph shows from January 1st to March 30th the time series of millimeters of snow water equivalent, It's just rising and falling. You can't see the net effect in this plot, but you interpret that from the time series. Then there's a snow gauge, and here's the weekly snowfall. And then if you take the difference between what was caught in the canopy for that week relative to the snowfall, then you find out the interception efficiency. If you look at the interception efficiency, you can see that it generally tends to be around this 25% level, but there are some values that are really high. The highest levels are associated with the smallest snowfall. And so for those of you who took HYD 143, this should be very familiar to you. This is the innate storage capacity of the tree, the canopy plus the trunk, if there's anything hitting the trunk. And that's a relatively small capacity. Once that's overwhelmed, you tend to get a large amount of throughfall. But on average, so you have about 25% for both of these species. You could also see that there are times when it gets to be quite warm, and you can have more or less snow during those warmer periods, so that is there too. So the intercepted percent is inversely proportional to the initial load. So if you have a lot of snow already filling up the storage capacity, then you're not going to be able to hold as much. And then the higher the snowfall amount, the less storage there's going to be. Now, to me, this is a little bit of a surprising result because you'd think that as snow is accumulating, you would be filling in the air spaces in the canopy and bridging them, and then you could actually be increasing that through time. So this data doesn't have high enough resolution to be able to see that effect. But I wonder, if you actually had, say, instead of you doing it this way, what if you used like high-speed video, and you watched a section of a tree, you had a good lighting on it, and you saw the snow as it's moving through. You could use particle tracking to see every individual grain. And my guess is that as snow accumulated, it would close up the pore spaces between the canopy, and you would see less and less snow getting through. So these are the ways you have to try to think, use critical thinking to decide if a hypothesis is well presented and if the data is clearly answering it. In this case, I see some interesting data. The results are being averaged to a weekly level. So you start to think, well, what's the real value of having this high resolution time series if the key question then boils down to weekly results? Maybe that's not the right technology. On the other hand, you have to be mindful, this is 1994, high-speed imagery existed, but today, of course, I could just take the computer I'm using now and practically get high-speed imagery out of it for free. So things change. And then this is the last study that I want to show you. It's an experimental study of tree branching effects, but not using trees at all. So in this case, what was done is they took boards, all of the same length, and then they cut them to different widths, and they cut them into different leaf or branch configurations with different amounts of pore space or openings. And then this last example with A, B, and C shows a complete panel of wood, one that's cut up into a branching configuration, and one with a finer articulation of branching. In addition to these different patterns here, you could see in the photograph that they use different slopes to see whether the storage would vary by slope. You could also see a weather station that was used in order to collect the ambient climatic data. So think about which of these, for example, which of these patterns A, B, and C would yield the highest retention of snow, and then which angle, horizontal, a mild angle, or a steep angle would yield that. And you could also see here some actual tree branches are hung up. I'll just show you one example of these results. You have, first of all, the three angles, the solid line, the finely dashed line, and then the other dashed line, going from 0 degrees to 35 degrees. So the flat horizontal angle yields the highest mean snow water equivalent. So it kind of makes sense. If something's flat, the least amount of chance for sloughing off of it. Then A is the solid board, B has the most gaps, and C is intermediate between those. So A consistently has the most capture, and B has the least. So snow is just falling through. Whether this ever fills in or not is hard to say, but still, the more projected area you have, the more total snow that you're going to collect. So this is an example of a very controlled experiment that's done very simple with a simple result, but it's very intuitive as well. So that concludes the lecture. Overall, what I've tried to do here is show you a variety of different methods, from the most manual point-based sensors, which give you a lot of detailed information but only at a few points, to the most spatially distributed remote sensing technique with MODIS that gives you very detailed, complex spatial patterns but gives you no detailed point information. I've also tried to show you several different examples of how snow hydrology is done experimentally, to give you a feel for applications of these different kinds of techniques. And so that's it for this lecture, and I'll see you back in class.